this video, I have a few multiple choice practice questions for you to help you with fluid dynamics if you need any assistance. Here, in the first one, it says 276 mercury has a density of 13,600 kilograms per meters cube. The second substance here is alcohol, which has a density of 800 kilograms per meters cube. And it says if the experiment requires equal masses of each liquid, what is the ratio of alcohol volume to mercury volume? So it wants us to find V alcohol over V mercury. Okay. So to do this, I think it's essential, hopefully you read carefully, that the problem states that both these substances have equal mass, which I think is essential for this problem. Alright, so I'm just going to go ahead and set up the function density is equal to mass over volume, only because this problem deals with density. It wants us to compare volume, and it says it's equal mass, so hopefully that triggers just to set up density is equal to mass over volume. I'm just going to apply this function a couple of different times here, one for mercury, one for alcohol. The first one I want to do is mercury. So the density of mercury is equal to mass of mercury over volume of mercury. But as you can see, the numerator doesn't have a subscript because it says equal masses. At this point, if you want, you can put a mass of mercury, but just know that the mass of mercury is also the same as the mass of alcohol because it said so. Okay, but I'm just gonna leave the subscript out because I like to leave things out, leave subscripts out when things are the same. All right, so here I need to isolate for V mercury because essentially you want a statement for V alcohol and V mercury, so you can set up this fraction. So on the left side, in no particular order, I just did mercury first. So V mercury is equal to the mass of mercury divided by the density of mercury. Okay. On the right side, I'm going to go ahead and set up the same process except it's for alcohol. The density of alcohol must equal to the mass of alcohol divided by the volume of alcohol. And once again, mass of alcohol doesn't have a subscript because it's the same mass as the mercury substance. All right. Here, I'm going to do the little switcheroo the same as I did on the left side. I need to get V alcohol by itself. So I'm just going to go ahead and multiply both sides by V alcohol at the same time. Divide both sides by the density of alcohol, or move the V up, move the density down. Okay. Now that we have these two statements, V for mercury, volume of alcohol, we can just go ahead and set up this fraction. So it wants V alcohol over V mercury. So I'm just going to do that. Right. I'm just going to say V alcohol divided by V mercury. However, the volume of alcohol is simply mass of the alcohol substance divided by the density of that, which is mass over 800. Well, what is the volume of mercury? Well, that is just the mass of mercury divided by the density of mercury, which is 13,600, which is given. But here we have a fraction divided by another fraction. So in math, when you divide by a fraction, you multiply the reciprocal. So here I kept the left side the same because that's the ratio that I want. It wants V alcohol over V mercury. So the left side stays the same. The top fraction gets brought down, and then the bottom fraction gets flipped because you multiply the reciprocal. So as you can see here, there's an m on the numerator, there's an m in the denominator, so that'll cancel out. Therefore, really, you're left with just 13,000 divided by 800, which will reduce down to 17 over 1. So the answer here is just 17 over 1. So the ratio for the volume of alcohol over the volume of mercury is 17 over 1. So that's it for this one. Okay, let's move to the next one. The next one here says there are two round tables in a physics classroom, one with a radius of 50 centimeters. If you wanted to, you could convert it to 0.5 meters. And then it says the other one has a radius of 150 centimeters, okay, which is 1.5 meters if you want to convert to meters. But I would just leave the units here because both of the units are in centimeters, so it will naturally cancel out. And it says here, what is the relationship between the two forces applied on the tabletop by atmospheric pressure? So the pressure here is just atmospheric pressure, so keep that in mind. So here are your choices, A, B, C, D, and E. So let's go and crack this out. For this particular problem, I'm going to start with pressure is equal to force divided by area. So here I'm just going to apply this a couple of times. So I can say the atmospheric pressure is equal to force 1 divided by the area of 1. Right here, P doesn't have a subscript because it says atmospheric pressure for both scenarios. Okay. So I'm just going to go ahead and keep F1 numerator. I'm just going to break A1 down into pi R1 squared because the definition of area is pi R squared. What R do I need? I need R1 since it's A1. All right, I'm going to do the same process for A2. So here, the pressure once again doesn't have a subscript because it's atmospheric pressure for both scenarios. Here, the numerator, what force? Force 2. And then the bottom is area 2. So likewise, I'm just going to keep F2 because essentially we're asked to find a ratio between F1 over F2. Here, on the bottom, I'm just going to break it up into pi R squared, R being R2. In this case, I like to do this. You don't have to. I like to say that R2 is 3 times R1. It's just by looking at the numbers. The first radius is given as 50, and then the second radius is given at 150, which is really, if you think about it, these are nice numbers. 50 to 150 is a 3-to-1 ratio. So I can say that the second radius is longer. How much longer? 3 times 50, right? So I can say R2 is 3 times R1. Again, you don't have to. You can simply plug values in at this point. I don't really care. But I like to write it in terms of variables so I can just cross things out when appropriate. All right. So therefore, the density for the second cross-sectional area here, the numerator, is just F2. I brought that down. Pi is brought down. However, wherever R2 is, I made a statement here. I said R2 is 3 times R1. So in parentheses, I replace R2 with 3 times R1, but I kept the square on the outside, right? Because the whole term is being squared. So if you think about it, 3 squared is 9, and then R1 is just R1 squared. Hence, that's where this 9 comes from, because 3 is squared. Then the R1 is also squared because the exponent is outside the parentheses. So make sure you distribute the exponent correctly to both terms. So as you can see here, I have a statement. Pressure is equal to F2 divided by pi times 9 times R1 squared. Well, what do I do with now? I have two statements for P. On the left side, I said P is equal to F1 over pi R1 squared. On the right side, I have P is equal to F2 over pi 9R1 squared. So because both these statements are equal to P, I can just set them equal to each other. So as you can see here, there's pi on the bottom. That will naturally cancel out. And there's an R1 squared. There's also 1 squared on the bottom right as well. So the only thing left here is F1, F2, 9, and a 1, right? So if you manipulate this function so that everything, because it seems like all the answers here are F1 divided by F2, F1 divided by F2. So in order to get this same ratio that is presented in the answer choices, F1's already on the numerator, so I can really divide both sides by F2. So I can just circle this F2 and move it down to the bottom left. When I move it though, there's still an imaginary 1 as a placeholder. Okay, so if you do that correctly, you'll get 1 over 9. So F1 divided by F2 is 1 over 9, because when I move the F2 down, it looks like F1 over F2, but once you move it, once again, there's a coefficient of 1 there, so please don't put in a 0. Alright, other than that, it matches with choice B. Here, in this one, I think this one's a little hard out of all three of them. It says here a horizontal pipe of water that at a flow rate of 0.02 meters cubed per second. So this is your Q. Okay, so it says flow rate, so pay attention to units. This is volume per second, so that's Q. It says at a Y section of the pipe, the cross-section area is 0.05 meters square. So once again, meters square is area, which is consistent here with what they're given. And it says the pipe narrows to an area of 0.1 meters square. It says assume ideal flow, or the flow is an ideal liquid, whatever you want to say. And it says which of the following is most near the pressure difference, okay, between these two section pipes. So here's a diagram to help you visualize. So keep in mind, we're trying to find the pressure difference, okay? We're not trying to find P1, we're not trying to find P2, we're trying to find what the difference is in these two, so it's kind of clumped together. Alright, so to do that, I want to go ahead and point out this is a horizontal pipe, which makes it easy because referencing the center of the pipe from the very bottom, the height is the same on both sides of the pipe, okay? And here again, it says the pressure difference between, so notice here, I underline the phrase here, difference between these two areas, okay? All right, other than that, let's go ahead and apply Bernoulli's function. Here I'm applying Bernoulli's function because it asks for pressure difference. So the difference between P1 and P2, and it gives us like flow rate and it gives us cross-section area. So this right away triggers Bernoulli because I can go ahead and cancel rho GH1 and rho GH2 because referencing the center of the pipe from the lowest point, both these heights are the same. So here I have P1 rho 1/2 rho V1 square, and then on the right side I have P2 plus 1/2 rho V2 square. What I want to do with that, I'm just going to go ahead and clean this up a little bit. Okay, well, it asks for the difference in pressure. So I have P1 on the left side, I have P2 on the right side. To get that statement to be true, I need to move P1 to the right or P2 to the left. So I'm just going to go ahead and move P2 to the left. So I have this P1 minus P2, which is the difference in pressure, right? When you subtract something, when you subtract something, the phrase here is difference. So because it says pressure difference, you need to somehow manipulate so you have P1 minus P2 or P2 minus P1. Alright, so like I said, I made a choice. I'm just going to move P1 to the left side, so I have P1 minus P2. But at the same time, I want to move this 1/2 rho V1 squared to the right side. So I carry down 1/2 rho V2 squared, but then this is positive, so when you move to the other side, it must become negative. Alright, other than that, I highlight V2 and V1 because I don't know what those things are. I know what the density is. The density is given as 1,000 kilograms per meters cubed because it's water. So here, I just factor out 1/2 in rho because, well, they share a common term. You don't have to. I like to. Okay, so again, from the third line to the fourth line, you don't have to factor it out. I just like to factor it out because both these terms have a 1/2 rho. All right, so it triggers that you need to find V2 and V1. Well, how do you find V2 and V1? Pretty light work. The problem states that the flow rate is 0.02 meters cubed per second. So flow rate, by definition, is volume over time, or the cross-section area times the speed. Well, I'm going to use this definition instead of V over T because the area is given, right? Time isn't given to me. So I'm going to say Q is equal to A over V is the preferred function here. Well, what do I need to find? I need to find V1 and V2. So I'm just going to apply this function a couple of different times for the 1 for the Y area, 2 for the narrow area. So Q, so you notice here Q doesn't have a subscript because the flow rate through the Y section and the narrow section must be the same. Right? It's pushing the same amount of mass in the same amount of time. So therefore Q does not have a subscript because it's the same through both sections of the pipes. Alright, other than that, so I can say Q is equal to A1 times V1. Well, I need to find V1, so to find V1, I need to divide both sides by A1, and then the Q is given as 0.02 meters cubed per second. The area for A1 is given here in the wording. It says the cross-section area is 0.05 meters square. Once again, so the area is already given, so we don't have to do any extra work here. So if you simplify this on your calculator, you'll get 0.4 meters per second. So that's V1. So we're one variable down. Now let's knock out V2. I want to apply Q is equal to V, except once again, Q doesn't have a subscript because it's the same. Here, I know A2, so I need to find V2, but I'm also given Q. So same process, I need to find V2 by dividing both sides by A2. Q is given, A2 is given. So Q here, I'm just going to plug in 0.02 meters cubed per second because it's given. A2 is 0.01 meters squared. Well, I'm still going back and forth here on the third line. Okay, so pay attention to information given to you, and hopefully just move on with these types of problems and make it easy. So if you simplify that on your calculator, you'll get that V2 is equal to 2. So now that I have V1 is 0.4, V2 is 2, I can just plug it in, right? So you notice here on the left side, I kept P1 and P2 the same because I wasn't asked to solve for P1, I wasn't asked to solve for P2, I was asked to solve for the difference. So I need to keep it as P1 minus P2, okay? Because the difference is the symbol subtract. Here, like I said earlier, I factor out 1/2 in rho, so I'm just going to write the 1/2 times the density. But in parentheses, though, this is a 4 because V2 is square, and then 2 square is 4. So I already did square for you, okay? V1 is 0.4, 0.4 square is 0.16, so it'd be 4 minus 0.16 times 1,000 times 1/2. So if you do that correctly on your calculator, you'll get a value of about 1920 Pascal. Well, that would match answer choice E because it says most nearly. So 1900 and 1920, it's roughly the same. Okay. All right. I hope that helps. Stay nerdy. Don't be whack.